Good morning, mechanics. Good morning. Good morning. It's Saturday. It's a day off. It is first day of my vacation, and I am working on getting my ham radio license. So I wanted to do a little study stream because I've been cracking this book open um, during the night, like just before I go to bed, and oh god, the camera is just wiggling. Oh my god, it's because it's I have a hard time like getting it in a good spot. Oh no, oh no. All right, I'm gonna try not touch my chair to it. It's kinda awkward because like, I have a, I have, like, one of those octopus, uh, camera holders, so it, like, screws into the webcam, but it, doesn't stretch very far, and I think I need to get one of those, like, arms that can go a little bit farther, so it's kinda, like, at a weird angle, and I'm kinda, like, having to shift over my desk, and, like, you can barely see. Well, no, you can see it. You can actually read that pretty well. But it doesn't like to stay put. So I'm kind of struggling here, but we'll make do. We'll make do. So yeah, good morning. I lied. I said in the title I'm having my coffee, but I've already had my coffee. So I'm just sipping some water. It's a little bit rainy today, so it's giving me a little bit of a headache, so I'm just trying to hydrate and listen to some chill music. Big sipper. So yeah, so I'm like 3 chapters into the ARRL Ham Radio License Manual. So it's a comprehensive book on everything you need to know to get your technician license from the FCC. So there's like, you know, an introduction section which talks about like what the ARRL is, which is the Amateur Radio Relay League, which is the biggest representative of ham radio operators in the U.S. And then it goes through like Welcome to Amateur Radio chapter, talks about like what it is, what it means, what you can do as a ham radio operator, how to get your license. So we got through that. Chapter 2, radio and signal fundamentals. This is where the good stuff starts. So it talks about like what are radio waves. And that's something that like I've seen in, educational programs and studies before, but like I've never really buckled down and like actually looked at like, okay, this word means this, like a frequency is this, and this is how you calculate wavelengths and things like that. So it goes through all that. So I'm enjoying the learning process there. Start to get into the real meat here where it talks about like the different bands represented in the radio spectrum. And that's very important to know. Very important to know the different frequencies, bands, very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extremely high frequency. So the main ones we're concerned with in amateur radio are generally high frequency, very high frequency, ultra high frequency. And then there is some stuff going on in medium frequency too. Um, so working through that talks about like just the general radio spectrum and really like a lot of this stuff starts to make sense when you think about it on just one straight line from left to right, right? So like at the very low frequency below 20 hertz, sorry, below 20 kilohertz is audio. So this is like what we can hear with our ears. And then as it gets higher, it goes into the radio spectrum, which is what we can't hear, which is permeating through the world. And then after the radio spectrum here, you get into the visible spectrum. So you get into the infrared and then, your colors, photons, all that stuff. So very, very cool learning this like for real this time instead, like I have to learn this for testing purposes, right? Um, and then this section's really cool talking about like the distance these wavelengths travel and um, how to calculate the length of a wavelength in meters. So the calculation for that is 300 divided by the frequency in megahertz because 300 is the speed of light, which is close to 300 million meters per second. So the actual calculation down here, the raw calculation is lambda in meters, which is the wavelength, is equal to 300 million meters per second divided by the frequency in hertz. But of course, you can boil that down to lambda equals 300 divided by the frequency in megahertz, because mega is in the millions. And you can see that in the standard model here, the International System of Units. Where is it? Mega is 10 to the sixth power, which is equal to a million. So this is all like super important stuff to know, because if you don't know your prefixes and you don't know the measurements, it's like, it doesn't make sense, right? It's good to know, like, you know, all this stuff. And this is things like, obviously many of us learn in science classes in school and whatnot, but it's like, if you're not using it day to day, like, you forget a lot of it. You'll probably retain some of it, but you'll forget a lot of it. So it's good to like refresh myself on these theories and all that. And it's also like just very basic radio stuff. Like, I don't know, like, we kind of know like the words like transmit and receive, right? So like transmit, you're transmitting a signal somewhere. Receiving, you're receiving a signal. But what's a transceiver, right? Yeah, you probably heard the word transceiver before, and it's like, duh, it's something that can both transmit and receive. It's just putting it's just putting transmit and receive together in the same word. It's a transceiver. It does both. So anyway, sometimes you get those little like, oh, not like mind blown, but like, oh, I see now. I didn't know that before, because you just never thought about it. So anyway, that's chapter 2. Chapter 2 is all about signals and radio, the fundamentals. And then chapter 3 is actually like basic electrical theory. So you actually need to know a little bit of electrical theory to take your technician exam. So I picked up a lot of this stuff just by like tinkering around and learning a little bit about electronics. And I do a little DIY, like soldering and working on little, oh shoot. Well, thanks, webcam. Hold on. I gotta tie off the USB cable here. It's like gonna keep falling on me. Hold on one sec. All right. Get under there. The camera itself is so top heavy that it wants to like lean forward. But if I tie it off on a or slip it under one of the arms there, it should stay put. Anyway, so you need to learn a little bit of basic electrical theory, which is cool. Like, I like that, So far I've learned things like how to calculate voltage from amperes and resistance, ohms. So like, what is it? Like, current is measured in amps, resistance is measured in ohms, and then voltage it's the force of the electricity, right? Yeah, it's the electromotive force. So really interesting learning electrical theory that like amps is the current that's going through. So it's like the flow of the electricity. Voltage is the actual force, like the push for the electrons. And then ohms, of course, the resistance, it's how much resistance is being placed against that electrical flow. So if you know one of those two of the three, then you can calculate the other. So there's a really cool pie chart here, very simple. And like I've kind of like burned this into my brain now by doing some of the practice formulas. So it's like this chart, and then you put E at the top, I, and then R. So what you can do with this is like, okay, I want to know the voltage. But I only know amps and ohms. So to calculate the voltage, you just multiply amps and ohms together, and then you get the voltage. So that's why they're next to each other, because they're multiplying. If I want to know amps, and I have the voltage and the resistance, ohms, I can divide voltage by ohms and then get the amps. And then the same with ohms. If I want to know the resistance, take the voltage and then divide it by the amps. I think I got that right. Okay, the formulas are here. The formulas are right here. So amps equals voltage divided by amps equals voltage divided by ohms. Voltage equals amps times ohms. Ohms equals voltage divided by amps. Yeah, so I got that. So it's cool. There's a bunch of like practice calculations here to, practice like doing those questions. And you'll see the book has all of these like um acronyms here, or sorry, like index numbers. These are all actual questions that are on the technician license exam. So these are the literal questions that are on the exam. So, like, yes, you could go through and do rote memorization, which I have heard some people do to get their technician license, but I'm not interested in rote memorization. I hate memorizing. I think memorizing is stupid. So, I'm here to really like learn these concepts and, actually like think for myself cuz memorization just sucks. So anyway, so yeah, so I've done like a bunch of electrical theory learning. It's actually really not a lot. It's only like a handful of pages here and it's very basic simple concepts of electricity. So it's like not daunting at all. So it talks about like uh DC and AC, right? Direct current, alternating current, the concepts of pressure and flow where you have voltage and amps. They're talk about like circuits in a series versus circuits in parallel. And a lot of these concepts, like these basic concepts, are like really useful if you're doing like electrical work at home or like understanding the concept of like, well, if I attach this circuit to this circuit, what'll happen, right? So good stuff. How to operate a multimeter. This is actually really important. I actually own a multimeter. I've used a few times um, to like diagnose problems and also like even to put this microphone together. So the microphone I'm talking through right now, it was part of a kit. Well, it was a kit. The whole thing was a kit that I bought from what's it called, micparts.com. And I needed to solder it myself and put in a bunch of resistors and diodes and capacitors. And I used a multimeter to tune it because that's one of the last steps you have to do. You have to like tune the potentiometer, I think it is, with your multimeter to get the mic locked in, basically. So multimeter, very useful, very good to know. Good to know how to like not damage it either, because if you're on the wrong mode with your multimeter and you put a bunch of current through it, it could actually like bust the instruments inside. So very important you know what mode you need to be on. So handy stuff. And a lot of this is for like how do I like operating my radio, like if I need to like repair it or diagnose a problem with it. This is all like really important stuff to know. So the subchapter I'm on now is called components and units. So this is just describing like electrical components inside devices, like any devices really. Starts with like some of the basic components like resistors, capacitors, and inductors. And then I think it gets into like, what does it get into? Resonance, reactance, impedance. Yeah. So we're working our way through here. So I don't know if I'm going to like read any of this out loud. But if you guys have any questions, just like let me know. I'm actually going to put some like study stuff on the screen because it's handy. Oop. Sometimes I don't know why. Sometimes I feel like you can drag stuff into OBS and it'll appear, and then sometimes it doesn't want to do it. Oh, here we go. So this is one of the helpful ones that I was talking about before. And actually, I want to crop this. There we go. So this is that pie chart, which was volts, amperes, ohms. So we're gonna put this down here for now, so I can refer back to it. I hope you like the chill music. It won't be on the VOD because like I don't know if it's copyrighted or not, but we got some chill music to study too. So All right, so I'm going to start reading through. I love this. This measurement, Henry's. Inductors store energy in a magnetic field created by current flowing in a wire. That's cool. So these coils of wire store energy. This is called inductance, and it is measured in Henry's. I wonder who Henry was. I assume it's the physicist or mathematician that created the inductor or studied the concept of the inductor. That's really funny. I need to look that up. Inductors have values measured in nanohenries, microhenries, and millihenries. And henries, capital H is henries. I'm gonna look this up. I'm gonna Google this. This is part of the learning process, right? It's just like, wow, that's funny. Why is that the case? Henry unit. It's part of the SI, which is the International System of Units. The unit is named after Joseph Henry. I knew it. Oh, he was an American scientist who served as the first secretary of the Smithsonian. Okay. While building electromagnets, Henry discovered the electromagnetic phenomenon of self-inductance. What a badass. Transformers are made from two or more inductors that share their stored energy. Oh, so that's what a transformer is. I mean, I know like transformer, right? It transforms energy between, I believe, like two lines. Or that's how I understood it before. Maybe that was totally wrong. That's probably totally wrong. This allows energy to be transferred from one inductor to another while changing the combination of voltage and current. Right, right. So, like, there's transformers on the electrical poles before the electricity comes into your house because it needs to take, the higher voltage and process it down to come into your house and go to your electrical panel. For example, a transformer is used to transfer energy from household 120-volt AC voltage to a lower voltage for other uses, such as in electronic equipment. Okay. I'm going to keep, like, folding this up so you guys can see it as I go through. Okay, now we're talking about impedance. All right, this is getting into more like advanced concepts that I'm not that familiar with. In a resistor, AC voltages and currents are exactly in step or in phase. As voltage increases, so does current and vice versa. Capacitors and inductors, the relationship between AC voltage and current is altered so that there is an offset in time between changes in one and changes in the other as energy is stored, then released. That means voltage and current have a phase difference. Okay. Okay, so this is the important part. The combination of resistance and reactance is called impedance, represented by the capital letter Z, and is also measured in ohms. Radio circuits almost always have both resistance and reactance. So impedance is often used as a general term to mean the circuit's opposition to AC current flow. Okay. All right, now we're getting into resonance. Circuits that contain both a capacitor and an inductor are called resonant circuits or tuned circuits. If variable capacitors or inductors are used, the resonant frequency can be varied, tuning the circuit. A tuned circuit acts as a filter, passing or rejecting signals at its resonant frequency. Okay. Tuned circuits are important in radio because they help generate, pass, or reject signals based on their frequency. That makes sense. So that's like tuning into a frequency and only getting the signals that you want and rejecting all the others. So this is like, seems like very low level basic radio stuff. I'm just going to reread this again. In a circuit with both capacitive and inductive reactance at some frequency, the two types of reactance will be equal and cancel each other out, a condition called resonance. The frequency at which resonance occurs is the resonant frequency. Circuits that contain both a capacitor and an inductor are called resonant circuits or tuned circuits. If variable capacitors or inductors are used, the resonant frequency can be varied, tuning the circuit. Tuned circuit acts as a filter, passing or rejecting signals at its resonant frequency. Tuned circuits are important in radio because they help generate, pass, or reject signals based on the frequency. Okay. All right, now we're getting into diodes, transistors, and circuits. So these are the questions that are going to be asked on the exam. Like, which is true about forward voltage drop in a diode? And the exam questions are all multiple choice too. So that's good. I'm good at multiple choice. I'm less good at like, do the math and then like show your work. I hate that. I was never good at math. This is multiple choice is a lot easier. And a lot of this is just simple math. It's very basic. Which of these components can be used as an electronic switch? All right, let's just get into the chapter. It's a lot of questions. Wow, now I know what a semiconductor is. I like never knew before. So semiconductors, as this says, are materials that don't conduct electricity as well as a metallic conductor, but they're also not a good insulator. So they're somewhere in between. And apparently there's two types of semiconductors depending on the impurities within it. So like this is why silicon is used in computer chips because it's a very good semiconductor. When you put so it creates either n-type or p-type material depending on impurities. And if you put them into contact with each other, you get a p-n junction that conducts better in one direction than the other. Okay. This and other properties are used to create many useful electronic components, generally referred to as semiconductors. Okay. And these are types of components, the typical components. So we got diodes on the left and transistors up here. So I'm very familiar with these components, like working with them, recognizing them, because I've done a lot of DIY projects that require me to solder diodes and resistor and transistors and resistors. So I've done a bunch of soldering with like these types of transistors. So those are familiar to me. This as well, this type, and then all kinds of diodes. I've soldered like all kinds of diodes. Usually the smaller of the three here. That one's a big one. That's a big one. Loads of text. Lots of text. Get my keyboard out of the way here. So diodes only allow current flow in one direction. And if it seems like I'm going through this very slowly, it's because like I have to reread things a lot and work out the concepts in my head. Like I really need to fully understand the base level concept in order to fully process like what the word means, right? Like like I said, I'm really bad at just memorization. I can't I can't just memorize it and go, okay, I know it, right? I need to like really understand it and visualize it in my head. I'm a very visual type of person. So learning is difficult for me. But as if I'm invested in it and I like what I'm reading, like I'm like eager to learn it and understand it and interested in it, it becomes a lot easier. And usually that involves like a visual element. This is very dense, like all these descriptions of like what all these components are. This is going to require me to like really kind of nail this down. I might actually like write out a vocabulary key just to like help me study it a little bit more. Using a small signal to control or amplify larger signals is called gain. I'm familiar with gain, or I'm getting familiar with gain. So like you adjust the gain in your microphone, you can adjust the gain in your radio to get a better signal through your antenna. So I'm pretty familiar with those. Owen's I'm bouncing a lot. Let me let me adjust my bounce real quick. Such a bouncy boy. Let's tone it down. Yeah. Let's bring it down. There we go. I'm very eager today. Ah, two common types of transistors, BJT and FET. So it's bipolar junction transistors and field effect transistors. I've dealt with a FET before. I actually dealt with a FET inside my microphone. That was probably the most difficult part to work with because it's very sensitive, and I think I need to solder like four different components together, four different wires. And they're, talking about integrated circuits here. I've dealt with chips, integrated circuits in building keyboards. So I've soldered integrated circuits to boards before. Pretty cool. Okay, now we're getting into protective components. So this is like surge breakers and stuff. Fuses, yep. Why should a 5 ampere fuse never be replaced with a 20 ampere fuse? That is a good question. Why not? Know what I just realized? I realized that my alerts are probably not coming through when people raid me anymore. I forgot about that. I need to work on that. The audio alerts, I mean. Sometimes things like that just pop in my head and I go, oh shit. Need a sippa. Ah, water. Delicious. When replacing a fuse or circuit breaker, use one with the same current rating to avoid creating a safety hazard. Using one with a higher current rating, even temporarily, could allow the fault to permanently damage the equipment or start a fire. Okay. Oh, right, because all right, so if it's designed for a 5 ampere fuse and you replace it with a 20, if it exceeds 5 amperes, it might damage the components. That makes sense. Yeah, that makes sense. Speaking of gain, I'm gonna turn the gain down a little bit on my mic here. I see it's still topping out when I like go blah. Fuses blow by melting a metal wire strip seen in glass tube of the cartridge models. Slow blow fuses. This is so lewd. We're talking about fuses blowing and then and then slow blowing fuses. We do enjoy a slow blow, don't we, mechanics? We enjoy the slow blow. Slow blow fuses can withstand temporary overloads. They sure can. Until they can't, and then it gets everywhere. But will blow if the overload is sustained. Yep, that's true. Fuses cannot be reused. I don't know about that. Surge protectors limit temporary voltage transients above normal voltage by dissipating the excess energy of the transient as heat. Interesting. Okay. Lightning arresters have a similar function in the antenna feed line. They are designed to handle the much higher voltages and currents of a lightning strike. So, interesting thing, I did have some electrical work done in my house a couple of years ago. And part of that was the electricians installed whole home surge protectors in the electrical panel. And they are rated up to a certain voltage to stop lightning strikes or heavy surges, which is pretty cool. And I go down to the electrical panel and check on them every so often just to make sure that they're still working. They have like a little green LED in them. So it lets me know that they're still active and I don't need to replace them yet. They're relatively inexpensive too. All right, now we're getting into gatekeepers. Gaslight, gatekeep, girl boss. That's what we are. Switches and relay control current through a circuit by connecting and disconnecting paths for current to flow. Makes sense. Okay. This is where we're getting into like logic circuits, I think. This is an important concept. So the differences between the terms indicator and display. So indicator either shows on or off. So it's like a Boolean value. So it's like a green light if it's on and not, and then if there's no light, then it's off. So that's an indicator. A meter provides information as a value in the forms of numbers or on a numeric scale. And a display combines indicators, numbers, and labels. An LCD is used on the front panel of many radios and test instruments. Okay. Very, very extremely basic concepts that like we don't even think about like day to day, right? You're just like, the light is on or off, but that's actually called an indicator. A switch is operated manually while a relay is a switch controlled by an electromagnet. Oh. This this concept of switches like shouldn't be new to me, but it's kind of new to me and I'm kind of like, what? So we're talking about differences between switches. So there's single pole switch, which controls a single current flow, double pole switch that controls two separate currents. Okay. Each throw refers to a different path for the current. I feel like I need a diagram for this, even though it seems very basic what it describes, but like I'm having a hard time visualizing it. Let us go to the Google and try and see if there's a diagram online. Okay, I think I found a good one. Let's try this. Okay, so single pole, single throw, one circuit. I don't know what that means. NO or NC contacts. Oh, normally open and normally closed. Okay. Single pole, double throw, one circuit, changeover contacts. Okay. That makes sense. Double pole, single throw, two circuits, two different circuits. Okay. I guess they're like linked together. And then double pole, double throw, two circuits, changeover contacts. Interesting. Okay. I think I get it. It really doesn't need you to fully like understand this. It just needs you to like know know the differences between them. But I want to know. I want to know the concepts. I want to know exactly what this means, right? Are getting into schematics and component symbols. This is the fun stuff. This is where we get into these cool symbols. There's a lot here though. Well-grounded symbols. Figure 315 includes 4 different symbols for grounds, which can be confusing. The upper right ground symbol. Grounds. Am I stupid? Where is it? Grounds. Here it is. Okay. The upper right ground symbol represents a connection directly to the earth. Okay. Yep. It's got like 3 lines. Hamburger. Some circuits require a connection to the metal enclosure or chassis. The upper left-hand ground symbol. Okay. Kind of like a box, right? It's kind of like a box. The earth one, it's kind of I kind of think of that. So we're getting into like learning strategies here. The earth one kind of looks like layers of the earth, right? Like the surface layer, the rock, the soil layer, the rock layer going downward, right? The crust, the mantle. Some circuits require connection to the metal enclosure chassis, the upper left-hand ground symbol. The chassis may or may not be connected to an earth ground. Yeah, but that would be separate from the specific component that you're grounding. So connecting the component, grounding it to the chassis, and then the chassis could have a separate earth ground from the chassis. That makes sense. Within a piece of equipment, the triangular ground symbol on the bottom left generally indicates a connection for current to flow back to the power supply. Okay. So this is like in descending order here. This is like the biggest type of ground, and then the next largest type of ground, and then keep drilling down into the unit itself. This is usually referred to as a circuit common or just common, the common ground, okay? If an A or D is added to the triangle, the circuit has digital computing components such as microprocessors, as well as circuits that handle analog signals. By keeping the return connection to the power supply separate for each type of circuitry, the analog signals are kept free of noise. Okay, so if this has an A in it, I get it. Okay, so if it's A, it's analog. If it's D, it's digital. You want to keep them on the different ground lines back to the power supply, because if you combine them into one line and they start piggybacking off each other, it's going to produce noise. Interesting. That's really cool. Oh, here's the switch diagram. That's what I was just looking at. So single pull, single throw, single pull, double throw, double pull, single throw. So they're connected. They each go to like 1. And then double pull, double throw. Got it. And the switch controls the current from both of these at the same time, because it's only like one switch controlling both poles. This is cool. This is really useful stuff to learn. And the questions for this are: what is the name of the electrical wiring diagram that uses standard component symbols? What is the name of the electrical wiring diagram that uses standard component symbols? I don't know. What is it? Are we getting? Yeah, we're getting to that. Okay. So resistors have like the squiggly line here. So we got fixed potentiometer, adjustable or variable, varistor. Oh, I got some like acid reflux right now. It's like burning my throat. Capacitors, So there's like a break, and then there's like a break between them. Inductors make the most sense to me because they're coils, induction coils, and this symbol is like very, very coil like. Relays. I've seen these symbols before with the arrows pointing. Transistors. This symbol is familiar too, though I don't know how to read it. Okay, so they got like a key here: base, gate, collector, drain, emitter, and source. So these are like your FETs and your was it BJs? BJP? Let's go back to the transistor section. BJT, bipolar junction transistors and field effect transistors. Oh, it says it right here. Bipolar junction and FET. And diodes. Diodes, that symbol's very familiar. The arrow going into the line. I know that one. You see that a lot when you're working with those components. Batteries, okay. Wiring. Yep, I'm familiar with this. This is normal 120-volt wiring, right? So your wall sockets, ground, the bottom one. You got your hot and your neutral. That's an important symbol. Antenna. Oh, my arm's in the way. Antenna. Cool. To describe complicated circuits, engineers have developed the schematic diagram, or simply schematic. Schematics are a visual description of a circuit and its components that uses standardized drawings called circuit symbols. Okay. Don't worry that you aren't familiar with all of them, talking about the schematic symbols. Look for and identify circuit symbols for resistor, capacitor, inductor, diode, and transistor. Okay, I think that... Okay, so that's going to be on the exam. So we need to know... We need to kind of basically know what these symbols are, not all of them specifically, like... But try to identify the different symbols on a schematic diagram, right? So I think I can name a few here. So this... We'll go from the left here, right? So we have our input here. This means this is the chassis ground. That's the ground of chassis. This one is, ooh, is it resistor? No. Yeah, that's resistor, isn't it? Yes, that is resistor. Okay, I got that. Resistor. This is a transistor. This is, I believe, an LED or some kind of light. This is some kind of light. Let's go back. Lamps. Oh, it's an incandescent lamp. LED is actually... LED is a bit different. It's under diodes, right? Yeah. So that's a LED. It's got the arrow. This... Well, it looks kind of like an earth ground. Yeah, that's probably the earth ground. And this isn't our chassis ground. This is a chassis ground. What is this? Is it the earth ground? What's throwing me off? Wait a minute. Oh, it's actually a multi-cell battery. That's actually a multi-cell battery. Hey, hello. Hello. Oh my goodness. The Baldur's Gate team. Hello, Danshi. Hello, Moo. Hello, Kuro. Oh my god. And Moo, wait, who did I miss? Sorry. I know there's 4 of you. I'm dumb. Danchi, Moo, Kuro. Thank you guys so much. Thank you for the raid. I really appreciate it. Good morning. Good morning from well, it's actually almost noon here. Nice socks. Thank you. Thank you. Hello, Taco. Thank you guys so much for the raid. So I'm having a study stream here. It's Saturday morning for me. I'm finished up my coffee and I'm studying for my ham radio technician license. So we're the outfit looks so cute. Thank you so much. Thank you, Hux. Here, I know some of you guys didn't get to come to my I know some of you guys didn't get to come to my debut, but I did put up a condensed video, like a 1-minute video, um, with my outfit debut, and I'll show it to you on stream here. Hold on one sec. I'm actually kind of proud of this. I spent a little bit of time yesterday doing some editing. Where is it? I got like my Owen folder is like all over the place. So here, watch this. Watch this. We're gonna mute the study music for a second here. All right, we're gonna add the video. And then, oh my god, an ad break. Come on. When the ad break is over, I'll show the clip. I love when I get rated just before an ad break and I have no idea it's going on. Well, welcome guys. Thank you so much for joining me. Yeah, so this is just gonna be a really chill stream. Hold on. Let me add the video so it's ready to go. I'm nervous. Okay. Oop. One second. I wish I could set it to like monitor and output by default. My bad. Anyway, yeah, if you're not in the ad break. So yeah, I'm studying for my ham radio technician license. So I've gotten through the first couple of chapters, but now we're doing like basic electronics, electronic theory, electronic components and units. So I'm learning a lot about the different components that go into, you know, pretty much every type of electronic system. And this is important for understanding radios because if you need to like fix a broken radio or understand like what's causing like, you know, issues and like interference and things like that, it's really helpful. When you get radio operator certified, what's stopping you from streaming on the radio waves, becoming not boomer encrypted, blasting Denpa and Catboy content? You can be guaranteed there will be Catboy content on the radio waves once I'm ready for this. Hayum radio, lol. Hayum radio. Yeah, hamster radio. Yeah, we're gonna get our hamster radio license. Yeah, it's gonna be interesting. It's gonna be interesting. Like, I'm really excited to get my license and then buy a little radio and see what I can do, see who I can get in contact with. I've been watching a lot of videos recently on like Morse code, which is commonly referred to as CW, continuous wave. And that's like pretty difficult to do. It's pretty difficult to like get good basically at Morse code, get good, get a high words per minute. But I'm kind of fascinated by the concept. So we'll see. I'm going to concentrate on getting my license first and doing a little bit of radio content where like I, you know, use my SDR and I browse around the airwaves and, you know, listen to other people. And then once I get the license, start getting involved in like nets and the local folks that are broadcasting, and then I'll see what happens when we start working on like CW. So welcome back from the ad break. Sorry guys, you just raided into me and you got ads. So let me show you the the clip I made of my debut, my outfit debut. Here we go. Oh, why isn't it? There we go. I'm nervous. Okay. Whoa, what's this? Oh my gosh, they just keep going. Very nice, very finely groomed. Hello, thigh highs. Thigh lovers were so back. These very short shorts. It's shiny. It's my Oshi mark, the sparkle. Bare arms, black shirt, bare shoulders. Oh, and don't miss. And then ooh. It's a collar.
It's a collar.
Going into the final stretch here. Thanks for coming to my debut. 2, 1. Hi, it's me. Uh-oh, we got the ada. Are you ready? Ada. Cowboy noises? Yeah. Thank you guys. Thank you so much for the support. I'm glad you really like it. Yeah, I'm really happy with my new model. Truly an Awooga, yeah. I saw the Awooga in chat. I was like, oh shit. Did you guys see Big Ham's reaction? Let me add that actually. It's so funny. Hold on. Oh, where did I save it? Did I save it to my desktop? I definitely saved it in my Owen folder. Everything's like all over the place. Oh, is this it? This is it, yeah. Hang on.
I want to see your new outfit. You look cute. I see your thighs. Did I see thigh? I see thigh highs. Let's fucking go.
She gets so excited for the thigh highs.
This is why you should follow Owen. His thighs. Oh, baby. Follow. Oh, sheesh. Oh, we look good. This looks awesome. Oh, my neighbors probably hate me. I'm just hyping. Just follow Owen. It is why you should. I like the necklace too. This is nice. Wow, it looks so good. Ooh.
I agree with Big Ham wholeheartedly. Yeah. She's so funny.
It's awesome. He's cool. You guys should follow Owen for that reason.
She's so nice. She's super nice, super professional. I really respect Big Ham a lot. So having me raid into her at the end of my stream and getting the sheesh was really nice. It really made my evening. And of course, you guys all coming out and supporting me and watching me and stuff. So you can see those clips again out on my Twitter, and also my YouTube channel has the full VOD from the debut night. And I played a cool rhythm game after too. So yeah, go check it out. All right, so back to studying. So we're at this point we're using this schematic symbol diagram to figure out like what exactly is going on in these schematics, because this is going to be part of the exam. Seems like we need to identify different parts of it. So it's like where these numbers are, it's like you need to identify these in the multiple choice. Don't forget to put the BGM. Oh, thank you. There we go. We got our chill study music. Thank you so much. So, all right. So this one is number 1. That's a resistor. Number 2, that's a transistor. 3, that is a lamp, a light of some kind. Incandescent lamp. It's an incandescent lamp. And this is a battery. I think it's a dual cell battery and not a single cell. Multi-cell. Okay, single cell and multi-cell. They got an exam too. Yeah, you got to take the exam before you can get your license. So there's actually 3 licenses you can get in the US for amateur radio. So the first one is what I'm studying for now. It's the technician license. And it allows you to, let me get the diagram, hold on. It allows you to broadcast on certain frequencies. So there's very specific frequencies in the radio spectrum that are dedicated toward amateur radio operators. So this means like you can't use them for commercial purposes. You can't like take money to broadcast on them. So like you can't set up your own radio station and then like get money for it. It's strictly for amateurs. So for the technician license, anything with a T next to it, you can broadcast on. So like from 1240 megahertz, which is the highest, the 23 centimeter band, which is the highest frequency that has amateur radio frequencies on it, you can broadcast on between 1240 megahertz and 1300 megahertz. And then it goes like down the bands. So all of these are open to technicians to broadcast on. But then once you get down to the 10 meter band, which is like around 28 megahertz, you need to have a general license to broadcast on that. So general license is like the next level up. So that requires you to take another exam. But with a general license, you can broadcast on 12 meters, 15, 17, 20. This is very specific. I don't know anything about this. It's a max. You're limited to a maximum power strength. And then 40 meters, 80 meters between 3.8 and 4. The 160 meter. So this is getting like really low down here. So with a general license, you can do way, way more than a technician license. Technician license seems like more getting your feet wet, and the higher the frequency, the less range you get, right? So it's kind of like they're limiting you to say like, okay, like when you first start out, you can't broadcast more than like a few miles away. We don't want you broadcasting like all the way around the world, on shortwave frequencies, doing stupid things. They really want you to get your general license for that. So before you start stupidly broadcasting all around the world. But these bands, like these frequencies, these are getting into the lower frequencies that you can like bounce off the Earth's atmosphere and talk to people like with the right antenna and the right amount of power. I could talk to Mowo from all the way around on the other side of the world if you get a good enough bounce off of the Earth's atmosphere. And not a lot of interference. And what's really interesting right now is I don't know if it's still going on today, but there's been a big solar storm going on from the sun. So you've seen that there's been like aurora borealis popping up in the sky recently, and that's because of a solar storm, and that's actually disrupting a lot of what's going on in these lower bands. So it's become very hard for radio operators to get signals to go very far because they're getting interfered with from the solar storm. So that's very interesting. That like a lot of people don't know about that because it doesn't really affect their normal day to day. It's just like, ooh, I can look up at the night sky and see pretty lights, but it's actually like wreaking havoc on radio signals, which is interesting. Oh yeah, and the third level, the highest level of operator is amateur extra. So with extra, they get access to all of the ham radio wavelengths. So they can go to these like very specific between 3.6 and 3.7 megahertz. Yeah, it's interesting. All right, so where were we? Oh, we were looking at this schematic and trying to identify things. So one, this is a plug. This is a power plug. I need to know the exact term for it. What is it? AC wiring, 120 volt AC wiring. Okay. 2, this is a diode. That looks like a diode. I'm just going to check my work as I go because it helps me a lot. Oh, it's a fuse. It's a fuse. Okay, so that's a fuse. I mean, it literally looks like a fuse, like an actual fuse you would see. This is a switch. This is a single pulse switch. This is a the coil inductor. That's an inductor, but what type of inductor? A magnetic core inductor. Okay. 5. This is a resistor. No. That's not a resistor. Oh my god. That is a diode. That's a diode. So the arrow one, it literally says D1. So that's kind of a hint there. That's a diode. 6C. Capacitor? I think that's a capacitor. Man, it's been a long while since the last time I touched schematic diagrams. Yeah. I mean, like, I've only seen, like, kind of stare at these as like, oh, that's cool. I have no idea what's going on. And now that I'm actually, like, learning the different components, it's pretty cool that I can actually, like, read a little bit of them. Okay, it's a fixed capacitor. It's a fixed capacitor. 7, this is a resistor. 8, this is another diode. 9, this is a resistor, but there's like a little loop. There's a little loop going in there. So is it a potentiometer or... Because the potentiometer has an arrow going into the resistance symbol. I guess it is. It must be a potentiometer. Okay. And then 10, that's another diode, but what kind of diode? I don't know do I need to know like the specific types? I don't really know. I guess I'll figure it out once I start taking practice exams. The cool thing about the exams is like they just publish the answer pools, like the question and answers. So you can literally just like go take practice exams over and over and over again until you're comfortable with them. And I was saying earlier in the stream, like there are some people that just do straight up memorization. They just memorize the questions and answers, but like I don't do that. I want to understand the concepts and I want to learn because this is like fascinating to me. It's really fascinating. But they do the exam guide here, the study book, it gives you like the number of the question on the exam and then directly like, tells you the answer by putting it in the text here. So yeah, so let's go back. Antenna tuner. So we got the input here, the squiggly line, and then there's another capacitor. There's a capacitor here. There's an inductor here, and then the antenna here. So that's the antenna symbol. Schematic diagram describes complex circuits by using symbols and the symbols representing each type of component. Lines and dots show electrical connections between the components, but may not correspond to actual wires. These are diagrams T1, T2, and T3 that are used on the technician exam. Oh, this is literally what is on the exam. These exact diagrams. Okay. So if I learn these diagrams, which are very representative of all kinds of components, which is pretty nice, I'll get that. I'll get that piece really easily. Very cool. It helps that like I've done a bunch of soldering of like diodes and resistors and these types of components already. So I kind of have a visual in my head of like what they are, what they look like, right? So like there's photos of all the types in here. And I was saying earlier in the stream, like I've soldered diodes like this and I've done a few of the transistors here, some capacitors as well. I've never dealt with an inductor before. I'd never seen that. Good luck on the study. Thank you. I haven't studied for an exam in a very long time, a very, very long time. So like, it's kind of interesting, like getting back to like, how do I study? Right? Like what works for me? I don't really know. But so far it's like kind of just like reading the material, rereading the material, looking at the diagrams, and then I think just like taking the practice exams will get me ready. Will get me ready to take it. So I'm hoping to like I haven't set a date yet, but I'm hoping like probably like end of October I want to be ready for an exam, and then I'll schedule it with one of the local radio clubs. It do be like that for exams, yeah. Yeah, just keep practicing. And I was talking earlier, like I've learned so much about basic electrical theory. I have this diagram here, which I've kind of burned into my brain. So it's like how to calculate one of the three here, like volts, amperes, or resistance, if you don't know the other, right? So it's like the E here. Oh, wait. Yeah, the E, if you don't know volts, if you multiply amperes and ohms together, you can get the voltage. If you don't know the amperes, you can take the voltage and divide it by the ohms and then get the amperes. And then if you don't know the resistance, you can divide the voltage by the amperes and get the number of ohms. So I'm already kind of like burning those things into my brain and doing like practice questions on that, doing practice calculations. Yeah. Oh, I need a big sipper. Big sipper. I've been getting really dehydrated recently because I haven't been paying attention to my water intake, and I've just been like so focused on stuff, So I'm trying to get better at hydrating. I might have to get one of those silly hydrate redeems for stream, so you guys can remind me when to drink some water. All right. So where were we? All right, so we were looking at the schematic symbols. Don't worry that you aren't familiar with all of them. Look for and identify circuit symbols for resistor, capacitor, inductor, diode, and transistor. You should do a hydrated redeem. Yeah, I should. All right, so I'm going to read through some of this and shout out some things I find cool along the way. Okay, so resistors, like I thought, they're designated with an R, capacitors with C, inductors with an L. Okay. Because I would be confusing because we use I for current amperes. So obviously they wouldn't want to use I in this model. Diodes with a D, transistors with a Q. It's interesting that the lines don't necessarily represent a physical wire. It just indicates that there's a connection between them. So that's also an answer to a question there. This is just talking about describing on the schematic how connections are represented, which is pretty obvious when you look at it. They join in the dots up here. This is going to be good practice coming back to the schematic and just going through it a few times. I've already pretty much got it. Like, I understand pretty much all these symbols. I like the ground symbols for chassis, ground these components to the chassis. To make this schematic easy to read, inputs to the circuit are located toward the left side of the schematic and outputs are toward the right. That makes sense, yeah. Positive power supply voltages are located toward the top of the schematic, and ground or negative supply voltages are at the bottom. Tell you to go to an outside source here. They're like, go on our website and watch a video on how to read schematics. I don't think we need to dive that deep yet. That might be more in the general exam for the general operator. I don't know if they get even further into electronic schematics, but this is really cool. This is really helpful. I've been wanting to actually have this knowledge in my brain for a while now, and this is a really good opportunity to really learn basic electronics. Honestly, if someone told me hey, how should I learn basic electronics, I'd take the same path. I'd be like, get a soldering iron, get little kits that you can buy for $5 or $10 and just solder some LEDs and transistors and diodes and resistors together, and then get your get your ham radio license. Just study this stuff because this is super helpful for understanding. Oscillators and amplifiers. Okay, getting more advanced now. An oscillator produces a steady signal at one frequency. Oscillators are used in both receivers and transmitters to determine the operating frequency. In a transmitter, the output signal from an oscillator is modulated and amplified before actually being applied to an antenna. Okay. So this is a diagram depicting what's called a CW transmitter. That's for sending out Morse code. So we have an oscillator, which determines the output frequency, and then a driver, and then a power amp. And then in between the driver and the power amp is a telegraph key. So that's like on or off, right? Full signal or no signal. And then it goes out through an antenna. Telegraph key is used to turn the amplifiers on and off, creating the CW signal that is transmitted. So beep, 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 beep. The oscillator runs continuously so that its frequency remains stable. Okay. Cool. Okay. So again, the telegraph key, the driver and the power amplifier stages are keyed, switched on and off by a telegraph key. Okay. So it controls both, I guess, simultaneously. So now we're getting into modulators. So this is like modulating the signal. This is where we're getting into like transmission of speech along the carrier signal. The process of combining data or voice signals with an RF signal is modulation. A circuit that performs the modulation function is therefore called a modulator. Of course. That's obvious. The function of the modulator is to add the data or voice signal to an RF signal or carrier. The result is an RF signal. RF is radio frequency. A modulator modulates? No way. Yeah, right? An RF signal that can be communicated by radio. A demodulator circuit extracts the information from a modulated signal. Okay, so when you're sending, good morning. Yeah, good morning, Blinded Eye. So the modulator is modulating the signal to carry the data or voice. And then on the receiving end, the receiver has a demodulator, which takes the information out from the modulated signal. Modulation is discussed further in chapter 5. Okay. Oh, we're at the end of the chapter. Which of the following is used to convert a signal from one frequency to another? A mixer is closely related to a modulator. Mixers combine two RF signals and shift one of them to a third frequency. Mixers are used in both transmitters and receivers to shift signal frequencies for various purposes. This circuit should not be confused with an audio mixer that combines audio signals. Yeah, I kind of grasped that. Okay. If I recall right, they use modulation and mixers a lot in PC stuff as well. I'm sure they do. This is all like base level components that make up the basics of electronics, right? So that's really cool. I want more info on to understand this. I mean, they're just kind of telling you the definition, but I kind of want another example of like when this is used. Mixers combine two RF signals and shift one of them to a third frequency. Why shift one of them? Is it shifting one of the original RF signals, or is it taking the combination and then outputting that combination into a third? That's what I'm confused about. Because this text here doesn't really answer my question. It doesn't answer my question. Actually, time to Google it, right? Time to Google it. All right, so we're going to the Google. I got so many papers here now. Get out of here. Electrical mixer. No, I don't want I don't want kitchen mixers. I don't want kitchen mixers. What? Electrical mixer modulation is what I want to search. If I could spell. If I remember right, it combines RF1 and RF2 into RF3, and RF3 would have a different frequency to hold all the data. Yeah, that's what I was figuring out. Oh, here we go. Yeah, you're right. Frequency mixer on Wikipedia. Okay, so there's a diagram here, and it shows an input signal from one side, a local oscillator coming in from a different side, and then putting out an output signal. Okay, I think they could have worded this better. Whoever wrote this textbook, they could have written this better and maybe included a diagram as well, but maybe they just, it's not super important for the level of study we're going at here, so I'll forgive them. But yeah, thank you. That's helpful. All right, so now we're getting into the good shit here. Chapter 4, propagation antennas and feed lines. This is the stuff that I'm watching a lot of YouTube videos on this and like kind of researching like what are good antennas for the things that I want to do, right? So we're going to learn about how radio signals travel from place to place, basic ideas about antennas, how feed lines are constructed and used, and what SWR is. That's oh wow, I already forgot. It's like interference, like signal resistance. Shoot, I gotta Google it. Oh no, I was wrong. Standing wave radio. Okay, I was wrong. Standing wave radio. I haven't looked much into RF stuff. Most of what I know is PC related. Yeah, I mean it's all like interrelated too, right? It's all like interrelated. A lot of the same concepts kind of cross over. No piece of equipment has a great an effect has as great an effect on the performance of a radio station, whether handheld or home based, as the antenna. Okay, so we need to understand the basics of propagation, which is how radio waves get from one place to another. So these are the questions for the exam. What is the effect of vegetation on UHF and microphone signals? So it's like, fucking trees getting in the way. what are trees getting in the way due to a signal? Okay, cool questions. All right. We're gonna go a little bit further. Probably not too much longer. There's some other stuff I want to do today. I want to go out. There's like uh an art like event going on near me that I want to go check out this afternoon. So I might grab some lunch in a few minutes. And then there's also Ludwig's doing his streamer games today, and I want to watch that. I think that starts at like 4 p.m. Eastern or 5 p.m. 1 p.m. Pacific. All right, radio waves spread out from an antenna in straight lines unless reflected or diffracted along the way, just like light. And radio waves travel at the speed of light, which we learned in a previous chapter that you can calculate wavelength by taking the speed of light and then dividing it by the hertz. So the formula is 300 divided by the frequency in megahertz. So you can get the wavelength. So it's the length of the wave, right? So at the lower frequencies, you're getting wavelengths that are like very long, like 2 meters in length. That allows them to like go around objects and travel further. The distance over which a radio transmission can be received is called range. Right. This is interesting. Obstructions such as buildings and hills also create radio shadowing. especially at VHF, UHF, and microwave frequencies. Well, what does that mean? What is shadowing? Vegetation can also absorb VHF and UHF radio waves. Okay, so vegetation will absorb the waves, not even like block them or reflect them. It will absorb it. This can result in greater range in the winter. Yeah, because you don't have as many leaves on the trees or bushes. Precipitation such as fog and rain can absorb microwave and UHF radio waves, although it has little effect at HF, which is high frequency, which is like a lower frequency than VHF and UHF, and on the lower VHF bands. Okay. Just to go back, just to review the frequency bands. These are our frequency bands from left to right. So at 3 kilohertz to 20 kilohertz, that's the audio range. That's what you hear with your ears. So you hear the frequencies up to 20 kilohertz. Past that, you start getting into the radio frequencies. So it goes from very low frequency, that's 30 kilohertz to 300 kilohertz. Medium frequency, so that's 300 kilohertz to 3 megahertz, so 3 million hertz. That's where your AM transmissions are. So AM radio is in the medium frequency band. Then from 3 megahertz to 30 megahertz, that's high frequency. That's shortwave radio. So that's where the fun stuff happens. That's where the fun stuff happens. And we can like broadcast like really, really far. Then very high frequency, that's 30 megahertz to 300 megahertz. So this is where like TV, when there was broadcast TV, that's where it would be broadcasted from. And that's also where FM radio is. And then above FM radio, this is where like the airliners broadcast. That's where like the air bands are. There's also like satellites in there too. And then UHF, 300 megahertz to 3 gigahertz. So UHF TV, mobile phones. 3 gigahertz to 30, that's super high frequency. And then 30 gigahertz to 300 gigahertz, that's extremely high frequency. So the 2.4 gigahertz and like 5 gigahertz, which is where like your I believe like Wi-Fi is broadcasting from, and a whole lot of other stuff is like in this range, like in here, just for like reference. This figure shows how radio waves can also be diffracted as they travel past sharp edges of large objects. That's interesting. Diffraction is a really interesting concept to me, because I know that also has like to do with like radar and like bouncing off of like jet fighters and airplanes and things like that. And that's why like the stealth bombers, right? Like the B-2, and I believe it's what, the F-114, the Nighthawk, they have like those sharp edges on them because it increases like, it helps their like stealth profile. Because I think it's probably related to this, diffracting the radar waves being bounced onto them so that they don't come back. This type of propagation is called knife edge diffraction. Refraction is another type of propagation. Okay. Okay, this is where you bend the radio waves in the atmosphere. By bending signals slightly back towards the ground, refraction counteracts the curvature of the Earth. This is the cool stuff. It allows the signal at these frequencies to be received at distances somewhat beyond the visual horizon. So obviously, right, we all know the Earth is curved unless you're a fucking idiot. Unless you're a fucking idiot, the Earth is curved. The Earth has curvature, right? So if you try and broadcast in a straight line, it's going to hit the ground at some point, right? Or no, it's not going to hit the ground. It's going to go off into space, right? Or, you know, outward, right? But if you bounce the signal, you curve it off the atmosphere, it goes back towards the ground, you can counteract that curvature and contact people that you wouldn't be able to see visually. The Earth is as round and smooth as my brain. There you go, Hux. There you go. Radio signals arriving at a receiver after taking different paths from the transmitter can interfere with each other if they are out of phase. Oh, okay. Even canceling completely. Interesting. This phenomenon is known as multipath and can cause the signal to become weak and distorted. So if it's bouncing off of different, if it's refracting differently, the signals are coming in at like different times. So they're out of phase, right? So we learned about out of phase earlier in signals, and I keep referring back because like I really like to connect all these concepts together. So this describes like phase and how signals can become out of phase. So now we're learning about like what that means. Like if they're out of phase in this type of instance, it's not good. Irregular fading, even when the reception is generally good. Okay. Moving your antenna just a few feet away may avoid the location at which the cancellation is occurring. Reorienting the antenna may also help by making one of the interfering signals stronger or weaker. So, like, this tells me that, like, even though your antenna, if you keep it in one place, depending on what's going on in the world and, like, the weather and everything like that, may affect your signal, right? And they're saying that, like, moving your antenna around and choosing a different location may assist depending on a lot of different factors, which is interesting. Because dead spots from multipath are usually spaced about 1/2 wavelength apart, VHF or UHF signals from a station in motion can take on a rapid variation of strength known as mobile flutter or picket fencing due to multipath propagation. All right, so that's if like you're in a car or a train or something and you're broadcasting. These are the types of things that can happen. Distortion caused by multipath can also cause VHF and UHF signal data signals to be received with a higher error rate, even though the signal may be strong. Okay. Oh, this is some crazy stuff. This is talking more about um how frequencies in the air or in the atmosphere can be assisted by the weather, variations in the weather. And it's talking about like temperature inversions create layers of air next to each other that have different characteristics. That's crazy. The layers form structures called ducts that can guide even microwave signals for long distances. So this is all referred to as tropospheric propagation, abbreviated as tropo. Tropo is regularly used by amateurs to make VHF and UHF contacts that would otherwise be impossible by line of sight propagation. Tropo contacts over 300-mile paths are not uncommon. That's crazy. So normally you wouldn't be able to broadcast that far, but if the conditions are just right in the atmosphere, you can go much further. That's so cool. Now we're talking about the ionosphere, so this is the stuff I was talking about where you bounce the signals off the atmosphere. So the ionosphere is from 30 to 260 miles above the Earth. That's a huge range. I didn't know that. Because when I think about like layers of the atmosphere, I think of them as like pretty thin. Like they're just like walls in my brain. But this is actually like a huge range. UV light. So this is like the ionosphere gets charged by the sun through UV light. Okay, so they positively charge the ions from the gas atoms, and those ions and electrons cause the ionosphere to be weakly conducting. Okay. Oh, there's another figure. Oh, okay. So we're gonna get to get to this to show you what the layers of the atmosphere. Also, love how the dust mat kind of matches your jacket. Yeah, yeah. So this is from Mintlodica, and Mintlodica is a keycap designer, and she's done quite a few designs. She does the magical girl designs. She's kind of like one of the first to make like um, really nice, cute. What do you call it? What's that type of palette called? Like, oh my gosh, the colors, like colors like this, pastel colors. So I actually have one of her cap sets. I'll show it to you. This is Magic Girl. This is this is Magic Girl. So it's like cute magical girl caps with just like a very nice pastel colors, pink and blue and yellow. She also she's designed other keycap sets as well, and one is like a blue. I think it's like the Millennial Magic set. And I often refer to that as like the magical boy set because it's just like very cute blue colors. It makes me think of a cute magical boy transforming. Anyway, yeah, it's really nice. They're really nice caps. I'd highly recommend them. But yeah, she's done like she has a few really nice desk mats, and this is like one of the smaller ones. It's been working for me pretty well recently because it allows me to kind of like move it on my desk so I can attach my steering wheel. The bigger desk mats are harder to get out of the way for that kind of thing. So okay. So UV light from the sun charges. We need more magical boys. We absolutely need more magical boys in cute magical outfits with lots of ribbons and bows and skirts. Radio waves can be completely bent backward toward the Earth by refraction in the ionosphere's E and F layers as if they were reflected. This is called skywave propagation or skip. There's a lot of vocabulary in here. Higher frequency waves are bent less than those of lower frequencies. Yeah, so the higher the frequency is, the greater the ability for it to just like penetrate through the atmosphere. So it's not going to get refracted or reflected. Wow. Okay, I didn't know this. Since the Earth's surface is also conductive, it also reflects radio waves. This means that a radio wave can be reflected between the ionosphere and ground multiple times. Each reflection from the ionosphere is called a hop. Reflections from the ionosphere allow radio waves to be received hundreds or thousands of miles away. Yep, that's how I can talk to Momo on the other side of the planet. Meow, meow, meow. Oh, all right, read that. Oh, wait, I didn't fully look at this diagram. So, signal source, so this is an antenna here. A barrier here with a sharp edge. So that results in interference. So that's knife edge diffraction. And then you have the shadow zone. The signal appears in the shadow zone. It's interesting. So I guess that's what shadowing is. Okay. All right, so we got some figures of the atmosphere here. So this is the ionosphere, 30 to 260 miles above the surface. And then these are like the different densities. The ionosphere is formed by a solar ultraviolet radiation. The UV rays knock electrons loose from the air molecules, creating weakly charged layers at different heights. These layers can absorb or refract radio signals, sometimes bending them back to the Earth. Oh no, your Twitch is glitching? Oh, it's me. It's me. I'm dropping frames. God, I can't go a single day without these issues. I'm sorry, guys. It just it just randomly happens. That's really shitty. It'll come back. I'm sorry. All right, this is getting more specific here. It's talking about like what layers reflect what frequencies at different times. We're so back. Yeah, we're back. Sorry about that. Just randomly dropping 5,000 frames due to due to my connection with Twitch. It's crazy how seasonal some of this stuff is. It's like, yeah, you'll get really good signal strength on these frequencies at this times of the day or this time of the year. And with years of maximum solar activity, like it's interesting how dependent it is on like literally nature, right? Getting into the aurora. The aurora, northern lights, is the glow from thin sheets of charged particles flowing down through the lower layers of the ionosphere. Those thin sheets, 50 miles or more above the Earth's surface, reflect VHF signals. Because the aurora is constantly changing, the reflected signals change strength quickly and are often distorted. Wow. So you can reflect radio signals off of the aurora, but it's tricky because it's always moving, right? Oh, this is really interesting. I've read about this too. The E region of the ionosphere is also home to meteor trails. A meteoroid burning up in several seconds that can reflect radio signals. Bouncing signals off of these ionized trails is called meteor scatter propagation. The best band for meteor scatter is 6 meters, and contacts can be made at distances up to 1,200 to 1,500 miles. Imagine that. Like, a meteor burns up in like a few seconds, and you can bounce a radio signal off of that ionized trail to send a message way, way further than you normally could. That's ridiculous. Like, how do you even plan for that? It's so random. This is a good diagram showing how the signals are propagating and being reflected off the ionosphere. Okay, we're gonna finish this page and then we're gonna call it because I got other stuff to do. I have no clue how people figure this stuff out. It's centuries of research and science and experimentation, right? I can only imagine like the first, radio operators to like send a signal way, way farther than they expected are like, I don't know how I did that, right? And then they have to like figure it out through like research and experimentation and calculation with math and just kind of understanding physics too, right? Like understanding how electrons work and atoms and the sun, charging the atmosphere and all that. It's wild. And it's not just like curiosity either. It's like necessity too, right? It's like when you need these technologies to work to communicate long distances or, even I mean, some of the time periods where we've advanced technology so much are during war, right? So it's like how do we get signals, to like units, you know, out in the field? How do we get those signals out to them from a very long distance away? Stuff like that. The highest frequency signal that can be reflected back to a point on the Earth between the transmitter and receiver is the maximum usable frequency, or MUF. MUF. How do you like that? How do you like that, MUF mechanics? How do you like my maximum usable frequency? It's pretty good, isn't it? The lowest usable frequency is called the LUF. Crazy. All right. I think we've learned enough for now. We're gonna come back to this later. I'm definitely gonna have more of these study streams because this actually helped me get through like 2 whole chapters since I started earlier. So thank you guys for coming. Thank you for the raids. Everybody who raided me, I really appreciate it. And Hux, thanks for sticking around and learning a little bit about radio. We're gonna keep going. We're gonna keep going, and we're gonna get our license. Thank you for the follow, Four Milks. Hey, Four Milks, hello. He's absorbing so much info. All right, we're gonna end stream now. Thank you, Milky. I'm sorry, I'm just ending now. But we'll be back. We'll be back later. Tomorrow. Wait, what's my schedule?
Oh no, my shoes!
Oh no, my legs. Me legs. There we go. Tomorrow. Do I have a schedule? Am I stupid? Wait, hold on. Where's my schedule? I don't know where it is. That's not it. Oh, I'm like, oh, there it is. No, that's the old schedule. You show up to stream with no legs. Yeah, I did, unfortunately. Here it is. Tomorrow, we're going to play Love Ghosty. This is a ghost dating game where we matchmake 60 different animals together. I don't, they're not all animals. I think there's like robots and some other stuff. But we're going to play Love Ghosty. This is a new indie game that came out, I think from a Tempura. I think there's a Tempura on the dev team. And I talked to Saku told me about this before it came out. She was like, hey, there's a new indie game coming out. You can sign up here. And yeah, I reached out to them and they very graciously sent me a review key. So I'm going to be playing that tomorrow. And I think Saku's playing it today. So if you want a little taste, you can watch her stream today. And then I'll be playing it tomorrow. Got that bisexual lighting? Yeah, love the bisexual lighting. It's so cool. It's so cute. And I'll give you a little treat before I go. You can look at my pink model with the pink booty shorts and the collar. All right, I'm taking off. Have a good rest of your day, mechanics. I will see you tomorrow. Bye-bye. 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 Bye-bye.